All right. I will begin. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask you to guide our steps today, help us to glorify you what we do, and we thank you for the break which is about to start, Lord. In your name I pray, Lord Jesus. Amen. All right. So today we are talking about integration. So, of course, we're going to be talking about integration of a function of 2 or 3 variables. But I'd remind you to start with that for one variable, we have the integral from a to b of f of x dx was equal to the limit as n goes to infinity of the summation I equals 1 to n of f of x sub I star delta x, right? This is the so-called Riemann integral, the definition. So here, the x sub I star is an element of x sub I minus 1 to x sub I, where x sub 0 is a, x sub n is b, and x sub I is actually a plus I times delta x, where of course the delta x is b minus a over n, right? So this was the setup of the integral of a function of one variable, right? So now we want to define the integral of a function of 2 variables, all right? And so we're going to start out by talking about, suppose we want to do the integration over some sort of rectangle, all right? And this rectangle R, it's going to be a comma b crossed with c comma d. Now this is the Cartesian product. So that specifically means x comma y, such that, x is an element of a to b and y is an element of c to d, right? That's what that means, the Cartesian product of these 2 closed intervals. So let me make my box bigger so you can see better. All right, so that was supposed to be, my corner got a little bit hinky there. These are both closed intervals. So this point right here would be a comma c. This point up here would be b comma d. Now these are points, right? I mean, this is by the way, this is just a, I don't know if you ever noticed this before, but you should notice it at some point. Our notation is degenerate, right? B comma d is a point, right? But in Calculus 1, it's also the open interval from b to d. So which is it? Is it a point or is it an open interval? The answer is, well, context. But anyway, this point over here would be a comma d, because it's at the top for y. This guy over here would be b comma c, right? So just to further emphasize what's going on here, this line over here is x equals to a, right? For c less than or equal to y less than or equal to d, that's this line, right? And over here you've got x equals to b for, again, c less than or equal to y less than or equal to d. That's the right line. Now the upper edge is what we got up here. We got y equals to b for a less than or equal to x less than or equal to b. And down here we've got, did I say y equals to b? What is it? That's d, right? Thank you. And then this bottom edge is y equals to c for, again, a less than or equal to x less than or equal to b. So those 4 curves bound this region, all right? And what we're going to do to define the integral over R of a function is we're going to slice and dice this interval into a grid, right? Like this. that way and also this way. Now they don't have to be squares, but you could take them to be squares. It doesn't really matter. I do want them to have like the same width for our construction. Like I do want them to be uniform. So my picture's not quite uniform, but I'm trying to make it uniform. So like what I'm trying to say is I want this width here to be delta x to be the same for everyone, and I want this height here to be delta y, and I want it to be the same for everyone. And so like delta x for us is going to be what? Delta y for us is going to be what? So to delta x, I take b minus a, and I'm going to divide by n. I'm going to suppose we have n boxes going horizontally. And I'm also going to assume we have m. So n is in nanu, m as in mommy. So that the delta y is d minus c over m, right? So assume m boxes horizontally and n boxes vertically. All right? In other words, I have mn total boxes, right? Now, in each one of these, I can define, all right, so like x sub I is going to be equal to, the same as it is up here, actually, a plus I delta x, and y sub j is going to be equal to c plus j delta y, all right? Those will define the grid points, all right? So like this point right here, for example, is x1, y1, all right? This point right here would be x2, y1, right? So like here, y sub 0 is c, and y sub m is equal to d. All right. So we have these, points that are defining the grid, and so like I'm just going to label. I guess I'll label the grid by the upper corner. So maybe this point right here is, let's say, x sub I, y sub j. All right? And so like this particular box right here, I'm going to think of this as the ijth area. Right? That I'm going to say that particular box there is the ijth area. And I want to think about a point in here. Right? And so like x sub I star, y sub j star would be an element of that area. Right? Now that area, that particular rectangle, I could also write as like the Cartesian product of two little subintervals, one for x, one for y. I guess it would be, this is x sub I minus 1 to xi, Cartesian product with y sub j minus 1 to y sub j. All right? So what I'm saying is, let me call this point Pij star. So like this point, Pij star, is a particular sample point in that subregion. All right? So with this setup, now I have the notation I need to define the double integral. All right? And here it is, the integral over R of, let's say, f of x comma y. Well, actually, forget the xy. Let's just say f dA is equal to the limit as n goes to infinity times the limit of the limit as m goes to infinity of the sum I equals 1 to n, the sum j equals 1 to m of f of x sub I star, y sub j star, delta x, delta y. So this is the definition of the double integral, all right, for a rectangular region. Now, what does this mean geometrically? Well, to try to understand this geometrically, I'd have to make a three-dimensional picture, right? You could think of like a three-dimensional picture for this, where, you know, you're thinking about maybe little skyscrapers over each region, right? And like, I can't draw it. So like this would be f of x1 star, y1 star times delta x, delta y. That would be equal to the little bit of volume over the 1, 1 spot, right? You can think about this geometrically as like the sum of the volumes of a bunch of skyscrapers, right? Where the area of each skyscraper is just delta x, delta y, and the height is defined by whatever the value of the function happens to be at the sample point. Now, of course, if that's negative, then we're going to count the volume as negative, right? So this double integral naturally calculates the area, the volume. It naturally calculates the signed volume bounded by z equals to f of x comma y and the region R. Right? Basically, it's the signed volume of the graph z equals f of x y over the rectangle. Okay, so that's one yes, sir.
Sorry, is the delta v sub 11, or what is that notation?
1, 1. Like 1, 1. If you want. I mean, you can put commas if you like, but
just like a, I, j.
Yeah. So like more generally, I could put I here and j here and ij over here. That would generally be true. I was just indicating like this particular one corresponding to the lower left rectangle. If you like imagine the graph out here. Okay, so this is how the double integral goes. The triple integral over, say, a box of f dv would be the limit as n goes to infinity, the limit as m goes to infinity, the limit as L goes to infinity of the sum I equals 1 to n, sum j equals 1 to m, sum k equals 1 to L of f of x sub I star, y sub j star, z sub j star, delta x, delta y, delta z. All right, here I'm supposing the box is something like a to b for x, c to d for y, and I guess I want to use e to f, but I've already used the f for the function, so I guess I got to use g. So e to g for the z. So like my delta x, as usual, b minus a over n. My delta y, d minus c over m. My delta z would be g minus e over L in my current setup. Oh yeah, thank you. Was that the question?
Yes.
Cool, yes. Now don't ask me to draw the picture here, right? Yes, sir.
So for the cross product, I forget.
Cartesian product, yeah.
Oh yeah, sure. When you do, like you just multiply out the first two and then go on and do that.
Well, this is a notation, a set theoretic notation that means we're looking at the set of x, y, z, such that x is in the first set, y is in the second set, and z is in the third set. That's what that notation means. And that notation that I just wrote, we could further explain what that means this first thing means that A is less than or equal to X is less than or equal to B. C is less than or equal to Y is less than or equal to D. E is less than or equal to Z is less than or equal to G. That's what those mean, right?
And do you multiply out the Cartesian product like dot product or?
No. No, I mean, this is a set theoretic construction. It's a set of ordered triples, so constructed. It's a set of points in three-dimensional space. I can't multiply them out, you know? So the similarity to the cross product is, and I might accidentally call it the cross product when I'm talking about it, but that's not wise. I should say Cartesian product, to be fair. So here, we're thinking about taking a three-dimensional space, a box, if you will, and chopping it up into subregions, and from every one of those subregions, taking a sample point, x sub I star, y sub j star, comma z sub k star, that defines the integral, right? So like, as these delta x, delta y, and delta z become very small, our choice of the sample point shouldn't matter, right? That's why we take the limit as n and m go to infinity up here. It's because no matter how we define, the sample point, whether we take the middle point or an edge point or whatever, in the limit, these differences should get washed away, all right? Now that's a theorem of analysis that I'm not going to prove in here, but that is true. These integrals are well defined, all right? Now, do we always just integrate, over rectangles or boxes? Well, certainly not, right? So what we want is for the integral to have like the following property. If S is the union of two sets, S1 and S2, where S1 union intersect S2 is empty or close to it, then we want the integral over S of f to be equal to the integral over S1 of f plus the integral over S2 of f. And here I mean this to mean two things, okay guys? Like I'm saying that's true for the area integral. I want this to be true for the area integral, the double integral, all right? But I also want this to be true for the volume integral, all right? So the integral should have this additivity, okay? And so essentially that's our we're going to define the integral to satisfy that. So like in principle, theoretically, right, if I had some kind of funky shape like this, and I wanted to form the integral over whatever this thing is, suppose it's a subset of the plane, what would I do? So what I do is I just chop it up into rectangles, because we already defined the integral over a rectangle, right? And see, I said it. I wrote the formula for two things, but we'd like it to be true for three things or n things or 1,000 things. See, I hope you can see the game I'm playing here. I'm just writing little rectangles inside my shape, right? See it? You could, I mean, make up any shape you want. You don't try to copy mine. That would be insanity, right? Don't do that. I think I've already spent enough class time on that. So, you see the idea here is we should say that the integral over the region of f dA is equal to the sum, over, say, I don't know, I equals 1 to n. Let's say find n of the integral over r sub I of f dA. Maybe this is R1, and this is R2, and this is R3, et cetera, right? That's the natural extension. Essentially, this is our definition of integration, is that we can keep chopping up into boxes, right? And again, I won't prove this, but it should be somewhat clear that if you take the limit as the number of boxes goes to infinity, whatever this is calculating, it should be uniquely defined, right? And whatever that thing is, we're going to define to be the double integral of this kind of shape. All right? Yep.
So is this, we're just trying to find the area or volume of the shapes that are really...
Yeah, I mean, we're trying to calculate. So here's, the graph z equals to f of x comma y, right? And maybe that's the graph over, if we visualize the set in the xy plane, maybe like this or something, right? Here's my r. So the integral over r of f dA is equal to, the signed volume under z equals to f of x comma y over r. Now, you won't be surprised to hear, I hope, that we don't actually take these limits, right? Thank God. Yes? That we do not actually have to calculate these limits. There is joyfully, oh man, I tell you what, I have problems with my brain. I've been reduced to pouring. So, there is a theorem that gets us around actually calculating these limits. But I think it's important to spend 15 minutes, 20 minutes of class time talking about these limits, because this is geometrically how we define the integral. All right? So it's important to know about that, because as soon as you ask the question that you asked, like what is it, the answer to that question goes back to this. This is what it is. But this is not how we calculate it. How do we calculate it? Well, theorem, the integral, the double integral, over the Cartesian product of a, b, c, d of f of x comma y dA. We can integrate, we got two choices actually. We can go a to b, integrate from c to d, f of x comma y dy dx, like that. And alternatively, we can integrate over CD, integrate over AB. Now this is one of those first is last kind of deals. And the order of the differential actually matters quite a bit. These are so-called iterated integrals. Iterated integrals. How did I get an n in there? I don't know. Iterated integrals. Right. And similarly, if you're integrating over a box, then the way you do it, this is a volume, so dV. Well, we can integrate AB, integrate C to D, integrate E to G, f of x, y, z. Now I want you guys to tell me how we have to put, if you understand the pattern for the top one, you should be able to tell me what to put next here. Like, see how it works? Which one? dz? Why is that? Why is there dz here? Because z goes with e and g, and that one comes first. So you do that first. Next, dy, because the next bound is the y bound. And we do that. And then finally, dx. Now, I'm not going to write it, but there are 6 possible orderings here. And the theorem of Fubini, the weak form of it, says that they're all equal, right? So this up here, this particular equality right here, this is Fubini, which is just an amazing name, incidentally. But Fubini's theorem, and Fubini's actual theorem is not exactly this. Fubini's theorem concerns when you can exchange the order of 2 infinite limits. The thing I'm erasing right now shows you that the integration is based on 2 infinite limits, right? So, like, to switch the dx and dy and dy and dx, in some sense corresponds to swapping these limits. And you might say, well, can't you always swap limits? Well, no. Actually, no, you can't. The other thing I meant to return to, and I forgot to, is I used a weasel word up here, or close to it. Do you guys know what I was getting at with that? Or close to it? Yeah.
Like if the areas share a boundary or something?
Yeah, if they just intersect on a boundary, if they just intersect on a subset which is of lower dimension. So like these intersect either on lines or points, you know? And the integration shouldn't care about deletion of a lower dimensional object. That's just like you guys remember from Calculus 1, when we're integrating basically over a line segment, if we delete a point or something, it shouldn't change the integral, right? Unless it does, of course, which is what? When would deleting a point matter? Well, if the integrand isn't continuous, right? If you're talking about something that blows up, right? Ignoring a point where the function blows up will mess you up, right? Like improper integration, points matter. But usually, if the function is continuous, you can delete a point. All right, so how do we do this integral? First of all, I violated my notation already. Double integral, right? So here we go. Let's do integral from 0 to 1, integral from 0 to 2, x y squared. And which one goes first then? dy. And this parenthesis I'm writing right now, that goes away soon. All right? Like, I don't always write that parenthesis, but training wheels for today, let's say. Or maybe just good practice always, I don't know. Anyway, the integral from 0 to 1. We're integrating with respect to y, holding x fixed is what's going on. So what's the integral of xy squared? 1/3 xy cubed, right? We have to evaluate that thing from 0 to 2, and then we integrate that, whatever that is. All right, so what happens here? We got integral from 0 to 1 of, I think, just 8/3 x, right? All right, so we can do that, right? This is what? 8/6 x squared, evaluate from 0 to 1. Answer, 4/3. Yay. It's kind of wild if you think about what this means. Like geometrically, we've calculated the volume, right? We've calculated the volume bounded by z equals to xy squared, which I don't even want to graph, right? For 1 less than or equal to x less than or equal 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 2, right? So you think about the volume bounded by these is that. I'm relatively sure it actually is the volume because that function is manifestly non-negative. So this is a genuine volume. It's not a sign, not negative.
Why would the area
volume. As I was just proving with the skyscrapers a second ago, the area integral calculates volume, just like the single variable integral calculates area, right?
What is dV? What are you calculating that?
We'd be calculating volume if we were integrating one. But if we were calculating something else, we're calculating, like, if the meaning of, if f is like, for example, mass per unit volume, then the integral, so suppose the function is like dm dv, so mass density. That's a good question you're asking. Then the integral of f dv over some box, let's say, would be the integral of dm dv over the box, yeah? Which would just be the integral of dm over the box. So what is the meaning? It's the total mass in the box, right? What's in the box? You want to guess? No? Okay. It's good. Could be a trap. Example 2. What if we were, say, integrating from over, I like 0 because it makes the things easy, but I'll do 0 to 1, 0 to 2. We'll do a triple one this time. 0 to, let's go to 3 this time. And our function will do, let's say, x plus the cosine of pi y plus z. All right? And I'll write dv here to get us started. I'm already regretting where I'm working. Oh well, it is what it is. So let's do integral. I want to get the x integral out of the way first. So integral from, integral from 0 to 3, integral from 0 to 2, integral from 0 to 1. I'm going to mix things up here, all right? I'm going to do the x first. And then I did the y, and then I did the z.
You can arbitrarily choose which one you first.
There are 6 choices. But yeah. At the moment, arbitrarily, because this is a box-like, a rectangular region. All right? I'll refer to these as we go on as constant bounds. Obviously, there's more to the story than this. Like next class, we'll talk about non-constant bounds, so-called type 1 and type 2 regions. You might remember those kinds of area calculations from Calc 1 or 2, where you found the area bounded by curves. We have to get back to that again. All right, so first order of business, we get what? Integral from 0 to 3, integral from 0 to 2, and if you don't mind, I'm just going to do the x integral. Oh, fine, I won't. This is 1/2, sorry, I was feeling guilty here, 1/2 x squared plus x cosine of pi y plus z. I'm going to factor that x out because I only really need one of them. Big parentheses, evaluate that thing from 0 to 1 for x, and we still got our y and z integrals. Let's see here, I'm going to move this over a bit. Does that look like Yoshi or something? Sort of? I don't know. So what are we left with after we actually do the x integral? So we've got integral from 0 to 3, integral from 0 to 2, and 1/2, right? And then plus cosine of pi y plus z, all right? dy and dz. All right, so next step, integral from 0 to 3. All right, let's focus on the inner one. We've got what? That's going to have 1/2 y minus, or no, plus 1 over pi, right? 1 over pi sine pi y. And then plus, well, zy. And I evaluate that from 0 to 2. Now, it's probably a good practice to put a y, like 0 equals to y, 0 equals to 2 equal to y here. That's a good notational habit to get into if you go back over here. Because that's one of the mistakes people sometimes make with these calculations is like evaluating the wrong variable. See, that's a real and present danger here because there's more than one variable. Anyway, so this gives us the integral from 0 to 3 of 1 over pi, yeah, you're way ahead of me. So sine of 2 pi minus sine of 0, also known as big fat 0, and then plus, well, 2z, right? Uh-oh. Shush. Silence. Sorry. So as I was told, this is 0. Woohoo! And we're left with then, doing the last integration in z, we've got z plus z squared. Evaluate that thing from 0 to 3, and lo and behold, we get ourselves a 3 plus 9. So the answer is 12. And so what does that mean? It means we've done a triple integral is what it means. So this is the first order of business, is getting down this iterative integral thing. And so usually what happens to me as I teach this material is by the next test, students are like, well, I understand how to do the integration. I just don't know how to set up the bounds. Well, yeah, that's kind of the hard part, is the bound setting up. You know, if you're given, basically, if you're given the bounds and you just have to calculate it, well, that's mechanical. And I do test on that because that is a skill that you need to acquire, right? But that is a less difficult thing than the more important thing which we need to learn how to do, which is how to set up the bounds. But you can't really see that today. So next class we'll start into the harder part. But anyway, that's it for today.